All right, can you all hear me okay? Okay, good. All right, so let's get started. Just some announcements. So I want to talk about exam 4. So we're a little bit behind in the class. So I think so exam 4 is scheduled on the 30th. And I know it's right after Thanksgiving. And I've done this a couple times in the past. Normally my exams are 3 chapters, especially in this course. So normally exam 4 is chapters 32 to 34. And if I'm sure I can cover everything through chapter 34 by next Wednesday. But my concern is the amount of time you have to study. So are you okay with me doing this? Of course, this test is worth, the last test is worth half the 4th test. So this is 19% of your grade. This is 9% of your grade. So are you okay with me doing that? Or do you want 3 chapters on exam 4? And I will say this, normally the chapter 34 problem is just one problem. You guys okay with that then? I mean, you're going to have 2 exams anyway, because we don't have a final, right? I'm not doing a final in this class. So your last exam would either be chapter 39 or it's going to be 34 and 39. So typically when I do a chapter 34 problem, because it's not, the way it's covered in this class, there's a lot of just equations thrown at you. So usually there's one problem that's given, okay? And so, so we'll do this for this class. And so this will be chapters 32 and 33. That would seem a little bit more fair to you folks. Okay, because the chapter 34 assignment is very short, and I usually give the class a lot less time to do it because the problems go pretty quick. Okay, the 39 was a bit longer. So we'll do that for exam 4. And just for those, not everyone's here, so if you know someone who's not attending today, please let them know. Okay. So in lab today, we'll talk about the transient circuits lab. That's going to be due December 1st. DC motor lab is 25th. Okay, and then next week in lab, I will talk about the last lab of the semester. It will be the longest lab. Okay, it's the LRC lab. It's pretty involved, but it'll be your last lab. Okay, and then homework 11 is due the Saturday after Thanksgiving. And so they'll give you a couple days to study for the exam. I know it's over the break, but okay. Any questions? So what I want to do today is start in chapter 11. I know there's stuff on LC circuits from the previous chapter that I haven't covered yet. I will do that in lab today. Okay. So I want to discuss AC circuits. And so what we're going to do is look at circuits that have resistors, capacitors, and inductors that are driven by a power supply, although we call it AC power supply. So I need to discuss what AC means. and you need to talk a little bit about the characteristic of AC, and then we can talk about the analysis of these types of circuits. Okay. All right, so the question is, does Ohm's law still apply? Okay, and it does. All right. And again, we're going to assume all our power supplies in this chapter vary sinusoidally with time. So we can write V is V sub m cosine omega t, or again, where V sub m represents the amplitude. Okay. So Ohm's law still does apply. V and I do change with time, and their instantaneous values follow Ohm's law, which means that if I set up this simple circuit with that voltage, then the current, which is going to be V over R, is going to be written as big V sub m cosine omega t over R. And this is just the maximum current. This is the amplitude of the current. Okay? And that's it. So it's very simple, and you can prove this by doing an experiment and measuring it, or you apply Kirchhoff's laws. Okay. So when the voltage drops equals 0, and you can easily see that V equals IR. So it's not. This is not a nothing groundbreaking. If you plot voltage and current on the graph, you plot them as a function of time, and maybe let me make this bigger, sorry, so everybody can see. You'll notice that the voltage and the current are in phase. So now what do I mean by in phase? What does in phase mean? Because this is going to be important for you guys to understand what phase means, and what in phase means, and what phase difference means. What does it mean that they're in phase? Well, look at the peaks in those two functions. Do they come at the same time? The answer is yes. The peaks come at the same time. The zeros occur at the same time. They occur at the same point in the function. And so there's no phase shift between the voltage and the current. Okay, so when I'm talking about the phase of a function that's sinusoidal, the phase is basically which part of the function you're at. So whatever this angle is, that represents the phase of that function. So if I have two functions whose peaks are displaced by this much, that distance in, oops, I don't know why I did that. That distance in angle is called a phase shift. So this is called a phase shift. We also use the term phase difference. That shift in angle between the peaks is called a phase shift or the phase angle. And this is going to be important when you take 215 and talk about waves. Okay, whether two waves interfere constructively or destructively is going to depend on the phase shift between the two waves. Okay, so make sure you understand that term, because that's one of those things that gets in the way of you understanding some of the concepts in physics. Okay. All right. And we're going to see that phase shift idea become important in a minute. So, we know that when you have a time-dependent current like this, the resistor obeys Ohm's law. Fine. Well, let me say something about the multimeter. If you use a multimeter and you're measuring AC current, what is it measuring? Okay. With the AC current that comes out of the wall socket, the frequency is 60 hertz. It means omega, which is 2 pi times this, is about 377 hertz. If this measured voltage is a function of time, you would not be able to see the values change. Your eyes, I think, could only see things change about at about 20 hertz, if I remember correctly. This would be changing 60 times a second. You're not going to be able to notice all the voltages. So it's kind of useless to measure voltage as a function of time on the multimeter. So what does a multimeter do? What does it display? Well, it displays some sort of average that's related to the average power in a cycle. Okay? It displays an average value that's related to the average power. It doesn't display the average in a cycle, because guess what the average in a cycle would be for a function like this? What's the average of the sine function over one cycle? What's the average of the cosine function over one cycle? What do you think it is? Yeah, there's zeros. Okay, so it's going to be meaningless to take the average of it. And you know, if you have a resistor in a circuit, the resistor is using energy. You can't say that the average energy used by a resistor is zero. And so what we do is we use the average power, something related to the average power, to display the voltage. Well, power is I squared R. Okay, so then what would the current look like? Okay. And can we write an expression for the effective current over a cycle? Well, this is going to be I max R I max cosine omega t squared times R, which is I max squared R cosine squared omega t. And remember that I max is V max over R, just in case you forget. Okay, so what I want to do is figure out what an effective value for R is. I'm going to base it on the P average. I'm going to base it on the average power. And so what I want to do is calculate P average over one cycle. And do you know how to calculate the average? Do you remember, I should say? I shouldn't say do you know, you should all know. Do you remember how to calculate the average of a function that varies with respect to any variable? In other words, the average power is going to be the integral of 1 over the period I hope you remember this from calculus. This is how you calculate the average power. My goal is to figure out an I effective over the cycle. Well, the question is, I mean, this thing is constant, this thing is constant. It's just this integral that I got to deal with. And remember, the period is 2 pi over omega. Okay, so I want to do this integral, and granted, I can actually go through and do this integral, but I'm going to kind of look at this kind of intuitively. I'm going to rewrite this, and I'm going to do this really without actually having to do the integral. Okay, I'm going to do this without actually grinding through and doing this integral. And my goal is to say that this integral is equal to I squared effective times R. I'll rename this when I'm done. Okay, but if I do this, then if I cancel the R's, I have this. And remember, and so this represents the average of the cosine squared function you see in the slide. So how am I going to do this without doing the integral? Well, let's look at the cosine squared function, and let's use a trig identity to rewrite it. I know that cosine average is 0. Cosine theta average is 0. And of course I know that the average of this function is not 0. Let me rewrite this using a trig identity. So now this is 1 plus cosine of 2 omega t with a 1/2 in front of it. So take a look at that function you see on the screen. Let me blow this up again. I just assume that omega t is theta there in the equation. So, see, I took Im, you're questioning about this Im squared. I'm taking the current squared, right? I squared R, so that means this has to be squared, right? Oh, I forgot this thing. I probably forgot that. Okay. Okay, so I want to take the average of 1 plus cosine of 2 theta times 1/2. So let's look at the first term. What's the average of 1/2 over a cycle? If I average 1/2 over a period of the function, what do I get? Don't I just get 1/2? Okay. What's the average of cosine of 2 theta over one cycle? 0. So then the average of this whole thing in brackets, this whole average here is 1/2. And so So that means I effective is 1 over the square root of 2 I max. And we're going to call this the root mean square current. So let me go here and write some values here. By the way, if you take 215, or those of you who are in 215, you've probably seen the term RMS. So what do you think the VRMS is going to be? What do you think VRMS is going to be? Same pattern. Yeah, it's going to be 1 over the square root of 2 I max. And again, if V has this function, all I got to do is square this, take the average of the function, I'm sorry, take the average of the square of the function, and then take the square root. That's an RMS. Oh, yes, sorry. Thank you. Thank you for pointing that out. Okay? Okay. So whether we're dealing with a current or a voltage, we can always easily find the RMS value. So basically IRMS or VRMS, all you got to do is really find the square the function, take the average of the square, take the square root, and then you have the RMS value. And so VRMS is going to be the same thing. So let me ask you this. If I'm giving a triangle signal, which can be generated, you can electronically generate that, but it would require a linear combination of sine functions to generate that. Now, before I do this calculation, I want to say something about the advantages of using AC current in your house as opposed to DC current. Does anybody want to guess why we use AC instead of DC? I'm sorry, Morgan, before I go on. You don't understand. You don't understand these two equations on the screen, on the board. I mean. So the average of this function is a half, so I put a half there. So I effective is I max squared divided by 2. And then I took the square root of both sides. Okay, so what I said was I renamed I effective as IRMS. I just renamed I effective as IRMS. It's just a renaming. Yes, there's an equal sign, sorry. Okay, I know. Sorry about that. Okay? All right, good. All right, so what I want to do is find the average of this triangle function. Yeah, so I guess the question was, why do we use AC currents as opposed to DC? One of the things you can do, and what Patrick said, is to deliver the energy over from the power plant, one of the things we can do because of AC current is we can use transformers, and we'll talk about transformers in this chapter. Transformers allow you to step up the voltage in delivering the energy to the house. When you stepped up the voltage, because of conservation of energy, the current's decreased. And so your I squared R losses are reduced, because if you step up the voltage, your current has to decrease. And so the I squared R losses go down as energy is delivered to your house, because they deliver the energy over high voltages until it gets close to your neighborhood, and then they step up the voltage, step down the voltage again, and you get more current. And that's true because energy has to be conserved. But there's one more thing. If you deliver DC, the average of a DC over a cycle is just going to be I squared R. I max squared R. The average of AC over a cycle is half of this. So see, if I have to conserve energy, correct? And power is I times V. So if I make this bigger, this has to get smaller if my energy is conserved. Well, the power plant is going to generate a certain amount of power, right? When generally the power plant will generate a fixed amount of energy. Correct. When the voltage is higher, the current will be reduced. Okay, but also if you use AC, the average over a cycle is half that of DC. Okay, so now having said that, let's do this example. So let me just show it to you very briefly. This is the signal, it's a triangle function. I want to find the average over a cycle. I want to find the RMS value over a cycle. So let me draw the function. This is t, this is 2t, this is 3t. I know they're not spaced perfectly, okay? All right, so this is V max. So I want to find the root mean square, meaning that I have to do the following. I'm going to take the function as a function, this function, I'm going to square it, and then I'm going to find the average of it, and then take a square root. Okay. I need to find, I need to write an expression for V sub m. So I'm going to look at this part because the y-intercept is 0. I can do it for each one of these, but I can do something similar for each one of these, but I want to do this one. The y-intercept is 0, so isn't it true that V is V sub m over t times the elapsed time? In fact, this is just the slope. Isn't that true? Well, we'll see if we get 1/2 out of this. Okay, so let's square this. And then let's integrate it over a cycle. The 1/2, 1/√2 is only for sinusoidal. This is not sinusoidal, and that's the point here. Right? Because how did I get the 1/√2? I took the average of a sinusoidal function. Here, I'm not taking the average of a sinusoidal function. I'm taking the average of something linear, actually. So this is not a tough integral because I'm integrating t squared. What's the integral of t squared? It's t cubed over 3. And this ends up being so V RMS in this particular case is V sub m over the square root of 3. Okay, so if I look at the average power loss in one cycle using this function, I get 1/3 instead of 1/2. So in fact, I would lose less energy using a triangle function to generate electricity. Why don't I use it? Why don't I use a triangle function as opposed to a sinusoidal function? Right? Let's see. That's right. It's harder to generate this because to generate this, you actually have to actually have to produce a linear combination of sinusoidal functions. And in fact, it's an infinite sum. Okay, but you can come close to it with enough terms in your sinusoids. Okay? I mean, to generate this, you have to take a sum because one can figure out what these guys are. So the value of these guys will tell you whether you get triangle functions or whatever. Okay. And there's a special name for these things. They're called Fourier series. And you can generate triangle, square functions, etc. with it. Okay. And if you're a chemistry major, engineering major, physics major, you'll learn about Fourier series at some point. Okay, question, how did the VMT become VMT squared when it comes out of the integral? You know what? I forgot to write the square here. Okay. Because I had it here and I forgot to put it there. So what does a voltmeter show for our standard outlet? The RMS voltage is 120 volts. And Vmax is 120 over the square root of 2, which is about 170 volts. So in your home, this is what's coming out of your socket in your home. Now, if you had a normal oscilloscope, not ours, do not do this with ours, okay, because you'll blow them, okay? If you had a normal oscilloscope, because our oscilloscopes that we have, let me grab it. These guys, I think, only go up to 50 volts, so don't use these to measure the voltage from the outlet, okay? But if you had a normal oscilloscope, you'd be able to measure, you'd be able to see the function, and you'd actually see the 170 volt peak. Okay, but don't use these at home, okay? Just do not use these at home because you'll blow them. In Europe, it's 50 hertz, but you know, whether you use 50 or 60 hertz really doesn't make a difference. Although I think in Europe they use 240 instead of 120. Okay. What we're going to start doing, how am I calculating the hertz? I'm not sure I understand your question. I'm not calculating the hertz, right? The voltage that comes out of the outlet is given to us. The power plant generates it, and so they generate it at 60 hertz. 120 volt is 60 hertz. 120 volt RMS is 60 hertz. That's what comes out of the outlet. But this function, this represents V as a function of time. Okay, that represents V as a function of time. From your house, or in your house. Is that okay, Morgan? Okay, well, I'll go on. So, we're going to be looking at what happens when you put capacitors and inductors in your circuit. Generally, what you have to do is apply Kirchhoff's laws and solve a differential equation, and then derive the equation for V as a function of time, or I as a function of time for that matter, and that requires a lot of work, and it's time consuming. So fortunately, there's a method that we can use for AC circuits, for sinusoidally varying signals that can make problem solving a lot easier. We're going to use a concept of a phasor to solve problems involving AC circuits where the power supply varies sinusoidally with time. Does that make sense? So what I'm about to show you only works with sinusoidally varying functions. Please make sure you understand that. And please make sure you are clear on that. And so I want to introduce to you what a phasor is. It's a graphical representation of voltages or currents. So, what is a phasor? It is a vector placed in a standard XY coordinate system. A phasor is used to represent a physical property that changes periodically, but not only periodically, it's sinusoidally. This will not work for any other type of function. Like the triangle function I show you, what I'm showing you here will not work with triangle functions, only sinusoidally varying functions. The length of the vector that we draw represents the maximum value of the property. This vector You imagine this vector rotates counterclockwise with the same frequency as the property it represents. And the instantaneous value of the property, which is voltage or current, is the projection of the vector onto the x-axis. And we can display more than one phasor in the same coordinate system. And the result's called a Phasor diagram. So essentially what we're doing is reducing this to a problem where we're just adding vectors. And again, I can't say this enough. It only works with sinusoidally varying functions. Okay. You will actually see this. You can actually see this used when you do optics. Because you can talk about, you can use this when you have electric fields that vary with time sinusoidally. Remember, these are not physical quantities. They are just used for visualization. So let me show you an example. On the left, I show you the voltage and current as a function of time for a circuit that just contains a resistor. On the right is a phasor diagram showing you V and I at some instant in time. The red vector represents the magnitude, the length of the red vector represents the magnitude or the amplitude of the voltage that varies with time. In other words, V max. The blue vector represents the amplitude of the current. The projection of those vectors onto the x-axis represents the instantaneous value, the value of V at a particular instant in time. Any questions on that? No questions? Okay. Because this is going to be important, because I'm going to be solving problems just using this graph. And boy, it makes problems really easy to solve. I don't have to apply Kirchhoff's laws or anything. And because V and I are in phase, you see that when you see the vectors drawn, the blue vector representing the current and the red vector or magenta vector, whatever you want to call it, representing the voltage, they're overlaid on top of each other. Does that make sense? So, like I said, no, the thing is, they don't have to be in phase. In this particular case, they are in phase. But its power is that we can use these when they're not in phase either, because all I'm doing is adding vectors. I'm going to do the inductor circuit and I'm going to do the capacitor circuit, and you'll see the effect. So I'm going to show you, one of the things I said was that these things rotate with time. And so I stole this from an instructor who developed this little thing. So I'm going to go through 2 cycles of this. So this thing is rotating 60 times a second. Of course, I'm not going to make it go 60 times a second. So this is what this vector does. There's the first cycle. And I'm showing you go through 2 cycles. Now, I need to say one thing here. And the person who created this used this convention. Our textbook is the only textbook that writes the voltage V equals V max sine of omega t. Nobody else does that. only our book. And so this simulation that you saw started with the voltage vertically, because that's what our textbook uses. But everybody else, all the engineering folks, write the voltage from the sinusoidal voltage. They all write it this way. So I'm going to do it that way. So why do I do it this way? I mean, we're off. Just a phase factor difference. Well, why do we do it that way? Well, it turns out, and this is related to the phasor, because the phasor diagram. We can represent this function in terms of a complex exponential using Euler's formula. I can represent this in the following way. This is a complex exponential using Euler's formula, and then you're just taking the real part of this. The real part of this is this. Okay? And if you plot this in a complex plane, this is the real part, and this is the imaginary. The projection onto the x-axis is your voltage. Okay? And so this phasor diagram comes from the fact that we can plot this in a complex plane, and we can express it as a complex exponential. That's where the phasor diagram comes from. And that's why I'm sticking to the convention that we write it in terms of cosine, because this is the real part of the complex plane, and this is the imaginary part. That's how one will normally plot it. Okay, and I'm going to use the graphical method is easy for simple problems. When you're doing more complicated problems, you actually have to write everything down in complex numbers. It's way fast. It's even faster than this, probably. We're not going to do things in terms of complex numbers. Okay, so first thing I want to do is a circuit with an inductor. And then we'll get to see how this works. Okay, so let's say we have a circuit with an inductor. That's our power supply voltage. Let's assume L is ideal. What do I mean by that? Yes, e to the I omega t. RE means real. So it means the real part, it means cosine, the cosine term. Okay, what do I mean by ideal? It means that the inductor has no resistance, or its resistance is negligible. Okay? So, the power supply voltage is V cosine omega t. And that's got to be the voltage across the inductor. So V sub L is L di over dt, which is V max cosine omega t. So di dt is V max over L cosine omega t. So di is V max over L cosine omega t dt. And so I got to integrate this. Right? I'm going to integrate this and I'm going to find I as a function of time in the circuit. And if you integrate cosine, what do you get? Then we don't have to worry about the constant of integration by putting those limits there. Okay, I'm going to get I is equal to V sub m over omega L sine omega t. Notice how this is written. It'll almost look like Ohm's law. It's almost look like a voltage over a resistance, doesn't it? And in fact, what I'm going to do is define x sub L as omega times L, and I'm going to call this the inductive reactance. Because there's a similar one for capacitors. Okay. So the voltage across the inductor can be written as I max times x sub L times cosine omega t. And this I max times x sub L has got to be V sub m. Now, I can rewrite this in the following way. Oops, small I. I can rewrite it in the following way. And I'm going to call this phi. And I'll call it the phase shift relative to the power supply. You get a better marker. Again, omega is just 2 pi times the frequency, right? Right, the omega that comes out of this when I take the integral, just omega 2 pi f. So let's plot voltage and current in a graph. And you'll see that the current lags behind the voltage by pi over 2. the current lags behind the voltage by pi over 2. So if I draw a phasor representing the voltage at some time omega t, the current is going to be behind the voltage by pi over 2, by 90 degrees. So for a sinusoidally applied voltage, the current always lags the voltage across the inductor. The current through the inductor always lags the voltage across the inductor by 90 degrees. Are we okay with that? The current through the inductor lags the voltage across the inductor by 90 degrees. Notice that V equals V max when the time derivative of the current is a maximum. Yeah, this is only in the case of the inductor. We'll do the capacitor too. So when you draw the phasor for the voltage across the inductor and the current through the inductor, you have to draw them 90 degrees apart. In the case of the resistor, the two are in phase. In the case of the inductor, they're 90 degrees out of phase. Does everyone get that? Okay. And so, like I wrote down before, the inductive reactance is just omega times L. Again, omega is 2 pi times the frequency of the signal. An inductive reactance really is a measure to opposition in changing a current. Right, it's a direct measure of the opposition to a changing current in AC circuit. And X sub L increases with increasing omega. Why is that? Why would X sub L increase with the increasing omega? Well, if omega increases, then that makes di dt bigger. It makes the change in flux bigger. And if you have a bigger change in flux, then your induced EMF is going to be bigger. You're going to have a greater opposition to the change in flux. Okay, so now let's take a look at the case where we have an inductor and a resistor in the circuit. We have an inductor and a resistor in the circuit. Okay, and all I'm going to do is draw the phasor diagram. And I want to show you how to do this very easily. Since they are in series, isn't it true that the current through them will be the same? Since they are in series, isn't it true that the current through them will be the same? Like this can actually represent a real inductor. So if the current is the same, I'm just going to draw a phasor diagram then. Let me draw a phasor diagram. Let me draw my coordinate system. And to make the drawing easier, I'm going to draw the current as a phasor along the horizontal axis. So let me draw the current like this. This represents the phasor, the maximum value of the current. I know this thing rotates as a function of time, but I can choose any point in time to draw this. I want to choose this one. But it just makes life easy for me. Okay, it's easier to draw this for me. Okay. So the voltage across the resistor, we know, is in phase with this. So let me draw the voltage across the resistor. Let me use red. And we just said that the voltage across the inductor is 90 degrees ahead of the current. And so these I'm just going to treat like vectors. And so the sum of the two will give me the power supply voltage. And V sub m, the power supply voltage, is just going to be the square root of V sub r squared plus V sub L squared. And notice, I'm only focusing on the maximum values. If I want the RMS values, I just take all this stuff and divide by the square root of 2. So I'm going to rewrite this in terms of current. I know that this is current times resistance. And this is current times impedance. I'm sorry, not impedance, but reactance. I got ahead of myself. And then I can factor out the I sub m and so I sub m is V sub m over this stuff. And I'm going to stop changing colors. And then I'm going to call this by the letter Z. And Z is the impedance. So I know the current, I can figure out the current through the circuit. And one more thing, this angle, this is cool. This angle, I call phi, is the phase shift between the power supply and the current. It's not 90 degrees anymore because I have two components in here. And the phase shift is easy. I can use trigonometry to find a phase shift. Phi is the inverse tangent of V sub L over V sub R. But because they both have an I in them, I can also write it as the inverse tangent of X sub L over R. And so my next slide I have everything you need to know regarding this circuit. So everything you need to know about this circuit is in that slide. So notice how quickly I was able to figure out everything. Otherwise, what I would have to do is to set up a differential equation and solve it. And it would be although it would be a first order differential equation, it would take a little bit of doing to solve it. Okay. V sub S is the power supply voltage. I'm just trying to show you that the sum of the voltage drops across in the last couple of lines, I'm trying to show you that the sum of the voltage drops across the inductor and the resistor equal the power supply voltage. Okay, so V sub S is the power supply, V supply. I'm just saying the voltage, I'm just calling the voltage V sub S. That's all. The reason why I use all those different letters is because those are all the different letters that are used to describe. I'm not using V sub M though in small letters, am I? Yeah, it's the amplitude. It's the amplitude of the power supply voltage. The amplitude of power supply voltage, we call it V sub M. I'm just showing that the V max, whether you're talking about V max across the resistor, okay, I'm just writing V max is equal to Vs. I'm just defining it, but it's really the power supply voltage. There's nothing more complicated than that. Questions on this? So I'm going to show you so the last thing I will do is the capacitor. And I want you to be able to do the diagram, a phasor diagram for the resistor and the capacitor. And it's really not that hard, okay? It's really not that hard. So, oops. If you write and there's a mistake in my notes here. The voltage across the resistor, if you write the voltage across the resistor as a function of time, they should have a cosine omega t minus phi in those equations. So there's a mistake in those in the slide. And I'll write it down in a second. I'll change pictures here. Hold on a second. So in those equations, they should look like this. V sub L times the resistance. Remember, this is the impedance. Should look like this, okay? And then the other one. And notice that if omega is 0, or as omega goes close to 0, then this term approaches 0, and all the voltage is across the resistor. So for low frequencies, most of the voltage is across the resistor. For high frequencies, as this goes to infinity, this whole thing, this ratio goes to 1. So for high frequencies, this ratio in here goes to 1. And so the voltage across the inductor approaches the power supply voltage. At high frequencies, that's what happens. Your voltage across the inductor approaches the power supply voltage. Low frequencies, the voltage across the resistor approaches the power supply voltage. So for low frequencies, we say that the resistor passes at low frequencies, and at high frequencies, the inductor passes. And so you'll hear the term low pass filter and high pass filters. And you'll see it in the textbook. So make sure you guys read the textbook, okay? And you should really come to class making sure you have read the textbook before I start the lecture. Because then things become a little bit familiar for you. Okay. I know I'm a little bit over, but I want to do the capacitor. Actually, there should be a minus sign here because when I take the derivative, there should be a minus sign in front here, which I forgot. And that has to do with the phase shift that's introduced. Okay. So let's just do the capacitor. So no resistance. We're going to do the same kind of use the same kind of logic as we did for the inductor by itself. So there's a capacitor, no resistor in the circuit. So the voltage across the capacitor is just going to be the power supply voltage. It has to be. So the charge on the capacitor, if you write the charge on the capacitor as a function of time, it's going to be the voltage of the power supply times C. And of course, your current in the circuit, you take the derivative of the capacitor charge with respect to time. Well, what do you get when you take a derivative of a cosine? Well, you get a sine. You also get an omega. There's two omegas there. It's a typo. There should only be one omega there. Sorry. And so you can write the current as the Q max times omega times the cosine of omega t plus pi over 2. So when you take the derivative of the cosine, you get a sine, but this sine is pi over 2 ahead of the cosine. And I put a plus there because of this minus sign that came out. So in general, we can write the voltage across, the current through the inductor as the voltage times omega c times cosine omega t minus phi. So let me go up on the board. So we had I sub c is equal to c times v m omega sine omega t. We can write it as q, because c times v is q. I forgot the minus sign. But I can also write it this way. And there you see a 90-degree phase shift again. Except that this time the current is going to be ahead of the voltage by 90 degrees. So I like to write everything in terms of, so it looks like Ohm's law. So I'm going to write it this way. And I'm going to call or define x sub c as 1 over omega c. So then I can write I equals v sub m over x sub c cosine omega t plus pi over 2. And we're going to call this the capacitive reactance. I better make this look like a C. Okay? So the phase shift is negative pi over 2 for capacitors, because this is relative to the power supply. So if you plot voltage and current on a graph, you will see that the current leads the voltage by 90 degrees. And so here's your phasor that represents the capacitor, voltage and current in the capacitor. The voltage across the capacitor and the current through the capacitor is represented by this Phasor diagram. So the current leads the voltage by 90 degrees. And so you should be able to draw the Phasor diagram for the RC circuit. Look. And I'll tell you how easy it is, because when I drew, and I erased it, but when I drew the Phasor diagram for the inductor, the inductor was up here. All you have to do the RC circuit is take this guy and point it downward. So if this was V sub L for the capacitor, and then you just keep and you just draw everything else. That's all you have to do. So I expect you to be able to do the Phasor diagram for the RC circuit. You got to know how to do that. Okay? So on Monday, I'm going to do the R, the L, and the C circuit. Okay, Monday I will do the RLC circuit. And I should be able to finish the chapter. And so this slide just has all the information I've already told you. Both, that's a good question, both X sub L and X sub C have units of resistance. Because remember that this has units of ohm seconds. And this has units of 1/seconds. So the seconds cancel, and you're left with ohms. So both have units, both X sub C and X sub L have units of ohms. This is called, X sub C is the capacitive reactance, X sub L is the inductive reactance, and when you combine the R's and the X's, you get something called an impedance. Okay, so on Monday, and actually in lab, I want to show you the RL circuit. Okay, I didn't have time to here, but I'll show you the RL circuit. So on Monday, what I'm going to do is this circuit. Oops. And our lab is based on your knowledge of this circuit. Resistor, capacitor, and inductor in series. Okay? So sorry I went 10 minutes over. I want to make sure I covered all the way up to the capacitor, because this will be the crux of our lecture. And again, you'll see, I'm just going to draw a Phasor diagram, and I'll get everything out of it like within minutes. Okay? And the triangle that I drew for the RL circuit is called an impedance triangle. And you'll see it again on Monday. All right, so I'll see you in lab.